So welcome to the next TNT seminar. For those who are new, again, I'll remind you guys of TNT, the Translational Neuroengineering Technologies Network. It's a group for people at Hopkins who, from any department who are interested in neuroengineering technology. And, we put on seminar events like this. We have a journal club. We put social events like the holiday party. And so it's a good way for us to kind of meet each other and get a little bit out of our comfort zone. Today we have Michael Beyeler speaking to us from UC Santa Barbara. He's an assistant professor in computer science and psychological and brain sciences. He's going to be talking to us about bionic eyes. So it should be very, very interesting for us. A couple notes before we get started on the talk. One, as you guys should already see, the talk will be recorded. So if you don't want to be a part of the recording, make sure to turn off your camera. Secondly, Dr. Beyeler said he's happy to take questions during the talk, especially if you have questions that are, points of clarification. He can do it right in the middle of the talk. So feel free to raise your hands in Zoom, and I'll call you out so you can ask the question. And then if there are deeper discussions that you want to have, we can talk about it afterwards as well. Last thing, as usual, we'll have a poll somewhere in the second half of the talk to kind of collect some information from you guys about who's attending and your interest in TNT. So be on the lookout for that, and please fill it out as it really helps us. So with that intro, let's have Dr. Beyeler begin.
Thank you very much, Mark, and thank you for inviting me. I'm excited to be here and tell you all about bionic eyes. And lastly, thank you all for coming. I know you're probably thrilled to go to yet another Zoom talk, but this was definitely the easiest way for me to participate in these series. All right, so today I want to tell you a little bit more about the so-called bionic eye, the retinal prosthesis more general, and what it is like to learn to see again. As you might be aware, blindness is a real problem that affects millions of people worldwide. In the developed world, the two most common causes of blindness are called retinitis pigmentosa and macular degeneration. Both of these are hereditary diseases of the eye, and they lead to progressive vision loss, either from the periphery inwards, as shown here on the left, leading to tunnel vision and eventual blindness, total blindness, or from the macula, the fovea, the center of vision outwards, in the case of macular degeneration. Now, although there is no cure for these diseases, researchers, of course, are trying to come up with ways to treat them. And so there are a bunch of really interesting approaches in development, one of which is gene therapy. Because there are faulty genes at work that cause these diseases, the idea is maybe you can inject a functioning gene into the eye, and that might either slow down or even reverse some of the disease progress. Another idea is to use optogenetics to make neurons that have never responded to light before now respond to light when you shine a laser on them. This could be useful if you, for example, make, ganglion cells in the eye photosensitive. You can shine lasers on them to activate them. And if you do that in a clever enough way, the brain might be able to see. And lastly, perhaps the most mature technology is the idea of an electronic prosthesis, a microelectrode array that is implanted either directly on the retina or in visual cortex. And it sends electrical current to activate the surviving neurons. And this is what I want to talk to about today. Now, this field of sight recovery it's not just science fiction, it's actually rapidly growing. There are already two devices out there that made it to the commercial stage, one developed by Second Sight in LA, and another one in Tübingen, Germany. Unfortunately, both of these devices have been discontinued as of last year or 2 years ago. COVID was not necessarily, well, it was a factor for some of these, but unfortunately now both of these devices are no longer available. But fret not, there are a lot of devices in development, some of which are already in clinical trials. promising one out of Chicago. It's an intracortical device. We have another retinal device developed at Stanford. And also internationally, there's a bunch of really interesting implants that might hit the market in 5 to 10 years. But as you look through the list of these names, you might notice that most of them seem to be biomedical startups, especially when I add these guys, the devices in development. And there are actually only a few groups that focus on basic research in this field. Here are a bunch of them. And I'm happy to also put UC Santa Barbara on the map, as I've started my own research group here. And what's kind of unique about us is that we don't necessarily have stock in any one technology because we collaborate with a bunch of different research groups, Hopkins being one of them. And so we are hoping to further our understanding of how these devices work such that all these technologies can benefit. Okay, this is a short video clip from a news report a couple years back that showcases the Argus 2 device developed by Second Sight. I don't know if you've seen this before, but I find it really interesting. So let me know if you cannot hear the sound. We tested it, but you never know. Here we go.
0 to the half ounces.
A talking scale.
Add salt, sugar, oregano, basil, tomatoes, and tomatoes.
And a computer helps
Sorry, that was me.
Sandy England, who is blind, make spaghetti pie.
Yes, one of my favorites.
4 decades ago, retinitis pigmentosa stole her vision. It's a genetic disorder that affects the retina's ability to respond to light.
I could see a menu and then slowly I couldn't see that menu anymore. And I couldn't see color. The color just faded away.
A single mom, she opened a bakery in her garage to make ends meet.
It was very tough, yeah. To raise 2 girls by myself, yeah, it was tough.
Her world has been dark for 40 years, until now. Doctors in Minnesota recently turned on her bionic eye for the first time.
Oh my gosh. Oh, wow. It was like over 10,000 light bulbs going off in my eyes. Ooh.
At home in West Jordan, she's learning to see in a new way.
You have something light on.
She sees shapes through electrical stimulation of the retina.
I could see you move just then. And I could see John standing right there.
Here's how it works. A camera on her glasses captures an image which goes to a battery-operated computer at her waist, then to a device on the outer eye wall connected to a microchip on her retina that sends the information to her optic nerve. Though she met her husband John back in 2002, she'd never seen him until recently.
I could see his neck, his chin, his cheeks, and his forehead. It is really wonderful to be able to see John again and my daughters.
It will give her an added dimension to what she's already been able to do. And it's another tool that she can use.
Not many blind people get to see their guide dogs.
Jet's a good girl.
But Sandy now sees Jet's silhouette and other ordinary miracles of life.
I could see the full moon for the first time in years. And the fireworks. I don't remember the last time I saw those. It was pretty exciting.
As doctors work to improve the bionic eye, Sandy and John enjoy new dreams and a new life. Heather Simonson, KSL 5 News.
Wow.
Wow, indeed. This woman has been blind for 40 years, and you implant a microchip in her eye, send some current, and boom, she can, quote unquote, see again. She describes it as a light show, right? Fireworks. She sees these flashes of light that come on depending on where she looks, and she can even see some shapes. So it's amazing that the technology like this could work. In the video, they already explained a little bit how it works. So this device, the Argus 2, comes with a pair of glasses, and the glasses have a small camera embedded here in the front. And so then the idea is whatever video the camera gets in, you send that to the chip. So you translate the video frames to a series of electrical pulses. Here's a an enlarged view. You can see this device has 6 by 10 electrodes arranged in a grid. And so the idea is that if you stimulate these electrodes in a spatially patterned way, then maybe you're able to produce useful vision. Now, this is basically the long shot to get there, right? There's a bunch of open challenges that we need to address as a field. First of all, there are surgical challenges, right? So you have to implant that thing in the eye or even in visual cortex. You have to be able to place the electrode array safely and securely, make sure it stays in place, and that it won't cause any damage to the nerve tissue. There are challenges with microfabrication, right? You need electrode materials that can safely deliver the needed charge, but not physically damage the tissue. You need watertight packaging of the electronics, biocompatibility, big issue. There's issues with electrical engineering. For example, currently we are limited to a certain type of pulses, the so-called balanced pulses, where whatever negative current you send in, you have to send in the same amount of positive current so that overall the net sum is 0. So most devices currently use these square wave biphasic pulses that over time sum to 0. You want to keep the current, the net current 0 because you don't want to cause any lasting damages to the tissue. And then to make this work, you need a certain amount of current, right? Which you need to deliver wirelessly, usually, because you have to communicate with the implant, and use that to stimulate multiple electrodes, usually at the same time. But what I regard as the biggest challenge of all is really the neuroscience behind it all. It is the challenge of translating electrode stimulation into a code that the visual system can understand. This pretty much requires us to understand the neural code of vision. We need to understand what happens when we stimulate different neurons at the same time in patterns and so on and so forth. Because as we'll see in just a little bit, if you just turn on electrodes all willy-nilly, sometimes people will not be able to make sense of it. So this is a big topic and what I want to focus on today. One of the simplest models of bionic vision is the so-called linear scoreboard model. It assumes that there is a linear transform from your stimulation to what we call the percept, the visual impression that people get. So let's say we have one frame of the camera. If we want to stimulate our grid, then one straightforward idea is to think of every electrode in the grid as a pixel in the image, right? And so if you stimulate a grid of positions on the retina, you would expect them to see a grid of luminous dots or phosphenes. This might not look very exciting if you only have 10 by 10 electrodes, but just give me enough electrodes, right? And eventually you should be able to produce useful vision. Unfortunately, this model does not predict real patient data. And I'll show you an example right now. Because we know this because we tested it. So we went out to Argus 2 patients, we turned on a single electrode, and we asked them to draw on the touchscreen what they see, to outline the shape. So here's an example shown. If you turn on one electrode, the patient would draw this arc, this line. That seems odd, right? So let's try that again. Trial 2, still the same arc. In fact, this arc always shows up when you turn on this specific electrode. And that's already remarkable, right? Because the person is blind, they can't even see what they're drawing. But over time, over different trials, they would always draw the same shape. We analyzed this a little more systematically. So here, just to reiterate, let's say we turn on one electrode. This one's called D3. Many times, you might always get like a vertical streak. And you can align these streaks by the center of mass and average them. So now you know on average, this electrode produces a vertical streak of a certain length. Of course, this is just one electrode, right? So let's look at the other electrodes in this implant. And now we see a pattern emerge, sort of. What's striking is that every electrode seems to lead to a differently oriented streak, right? But remember, these are averaged over trials, meaning that the shape is remarkably consistent over trials. It's just that from going from one electrode to another, you might get a totally different shape. I just saw a question pop up in the chat. Does the arc they see present a single arc pulse, or does it evolve from an initial point to a terminal point? Oh, that's a great question. Most often they see it as one flash of light. And that probably has to do with the stimulation parameters. Some people can see motion, so they might see one thing and then they see it moving over time, but most often it's a flash of light of a certain shape. All right, so this is just for one subject. So let's look at other subjects. And we see, again, a whole range of patterns, right? This first one actually uses Argus 1, the prototype. It has only 4x4 electrodes, but you see similar kinds of shapes, right? You have these lines, streaks, arcs, blobs, wedges, whatever you want to call them. But they're definitely not pixels, right? Maybe these here, maybe you call these pixels, but more often than not, they're not pixels. So what is the cause of these distortions, as we call them? Well, to understand that, we have to look at the retinal physiology a little bit. And you're probably all aware how light enters the eye. So it is projected onto the back of the eye, where you find the retina. If we zoom in on the retina, now there's a crosscut. We see different layers that contain different populations of neurons, right? Your first cells are the photoreceptors, the light sensitive cells, and they send, so they respond to incoming photons, path of light coming in from the bottom, hits the photoreceptors, and they transduce the signal into an electrochemical signal that is passed forward, passed on to the bipolar cells, some other cells in between that are also important. And then finally, the ganglion cells, which are the output layer of the retina. They send their axons through the optic nerve, shown here, to the brain. Now, in diseases like retinitis pigmentosa, you lose your photoreceptors. And so a straightforward idea is now to replace this lost functionality with an implant. If you place it right here where the photoreceptors used to be, this is called a subretinal device. You can also place it on top of the ganglion cells. So inside the eye here in the fluid, that's called epiretinal, or you can even go outside suprachoroidal. And important to note, the one I just showed you, Argus 2, is actually an epiretinal device. So you can see how it sits on the ganglion cells, on top of the ganglion cells. But not just the ganglion cell bodies, right? Also the ganglion cell axons. And that turned out to be critical. If we take a bird's eye view of the retinal surface, we see that these axons actually form various stereotypical patterns. So here, every line is a nerve fiber bundle extracted from one of 55 cadaver human eyes. And the trajectory of these bundles, they were aligned by the optic disc and the fovea. And if you do that, you see these stereotypical paths emerge. We can easily describe them as a spiral in polar coordinates. The equation itself is not that important. It's important to note here is that it only has two parameters. If you specify A and B, you can pretty much model any one of these fibers here. Another landmark that is important, will be important later on, is the raphe, the horizontal raphe. That's a place where you find no axon bundles. Why is that? Because if you're a neuron that lives right above the raphe, you would send your axon along one of these pathways to the optic disc. And if you're right below it, you would send it down here. Okay, now let's think about what would happen if you placed an electrode on top of these axons and you stimulate it with electrical current. You wouldn't just hit the ganglion cell bodies that live right below the electrode, right? You would also hit all the axons of other neurons that send their axons through this point in space to the optic disc. Where do all these neurons live? They would live to the left of this electrode, right? Because if you're a neuron over there, let's say this guy, you would send your axon along this pathway, and that happens to be the same bundle pathway as the neighbor, and so on and so forth. So now usually if you turn on ganglion cell, it's like a blob or edge detector in a certain spatial location. It signals to the brain, hey, I saw something and it was right there. But now you're turning on many neurons at the same time. So you're telling the brain, I saw something, it was right there, but it was also right next to each other and right next to each other and so on. So essentially what you're doing is you are drawing a streak, right? Because you're turning on all these neurons at the same time, and these neurons happen to live on the same nerve fiber bundle. So you're basically drawing this arc. Maybe that's why people are drawing arcs and streaks. But if that were true, we should be able to predict the shape, right, of the phosphene of the drawing as a function of where the electrode sits on this map. And sure enough, that's what we tried to do. There's only one problem, right? So now you have to map out these axons in vivo, which is really hard to do because the data we have to work with looks like this. So these are fundus images. You can get it before and after the surgery. And so sure enough, it's easy to detect the optic disc. The fovea is over here. But once you implant, of course, you can no longer see the fovea. So how are you going to find out where the implant sits with respect to the fovea? There's a bunch of different ways you could do that. One is to use feature matching, so a little bit of computer vision. For this, you would label landmarks in both images. And then you would try to find the coordinate transform to go from one set of points to the other. What this allows you to do is it allows you to register the images, put it in the same coordinate system. And so now if you label, let's say the fovea up here, you automatically know where the fovea is in the second image as well. That's shown here. So here we have a cross for the fovea, and then here the dot for the optic disc. There's a little bit more you need to do because the image could be rotated. You need to figure out the scaling factor. I'm going to skip over this. Essentially, what happens is we are able to place a simulated implant on a simulated map of axons. And now we know exactly where each electrode sits, what its retinal location is, and where the fovea is. All right, so if we're right about the axons, then the orientation of the drawing of the percept should be well aligned with the underlying fiber bundle, right? So let's look at an example. Here, again, averaged over 5 trials, you see a drawing. And even though it's blobby, you can see it's kind of elongated, right, along this axis. And we can use image statistics, so-called image moments, to calculate the orientation for this image here, which kind of looks like this, and overlaid on the map, you see, this is a pretty good match, right? This lines up pretty well with the fiber bundles. Here's another example. So now it's a triangle, but you can still see it's elongated along this path. And the line really long, it's a little harder because you could get different, because of the curvature, you can get different orientations. This is sort of like the average orientation. Still aligns pretty well, right, with this fiber bundle, and so on and so forth. So overall, this seems to fit really well. The problem is just, it's going to be off a little bit, right? These people have been blind forever. They can't see what they're drawing. And to get a perfect match is probably, that's not going to happen. So we're going to get some error, right? If you look at the orientation between the drawing and the orientation of the fiber bundle, there's going to be some error. The question is just, is this error smaller than what you would expect from any other placement on the retina, right? So we can do a bootstrap. We can say 10,000 times, for example, let's place the array anywhere on the retina. Let's calculate the errors you get, and then compare that to this distribution here, which is the true distribution of errors you get from this. All right, does that make sense? So let's say here you have some distribution of error. Now let's place the array somewhere else. Let's do the error calculation again. And if the axon map were right, then that error over here should always be larger, right, than what you get here. So long story short, you can do a bootstrap. You can check, 50 out of 10,000 times. Was your error larger in the other case, 50 than out of 10,000 times? If it is, you get a confidence interval. And so for this case, you can see the true distribution of errors was always smaller than the other one you would get from random placement. And so that's a pretty good indication, a statistical test to let you say, okay, we're fairly certain that what is causing these errors is actually the axon map. And if you place the array anywhere else, you would get much larger errors. This works well for this subject, but it also works well for the others we tested. So here again is the Argus 1 subject. That one is super nicely aligned. This might be the one I just showed you. And then 2 more. No, the last one. This is what I just showed you. And these are 2 more. And you can see that there is some error distribution, right? It doesn't always work perfectly, but overall, the bootstrap always showed you that this is the best you could do. Cool. That's one step. But what we really want to do is we want to be able to predict the shape, right? That would be perfect if we could predict what the phosphine would look like. And so for this, we need a more sophisticated model. If we go back to the scoreboard model, that's the idea that everything is a pixel. Then, of course, you could only predict circular phosphines. The only thing that might change is this radius, which we can call a rho. So now what we could do is we could use this map, threshold it, and compare that to a real drawing, right? And then we just need to find the row that gives us the smallest error between our predicted image and the actual image. A slightly more sophisticated model now takes into consideration the axons. So maybe you don't just need row, you also need a second parameter that describes how quick or how far current spreads along the axon. We call that lambda. And you still keep rho, which is how far current spreads perpendicular to the axon. So now you have 2 parameters, and you can fit them again to the patient drawings. What we really need to do is we need to find one set of rho and lambda per subject that explains the drawings the best. So this is a, excuse me, optimization problem, right? So we want to find rho and lambda that minimize the error between predicted and ground truth shape. And we can do this with a train test split. So we would only train on, in fact, all but 1 electrode. And then we would test our values of rho and lambda on the left out electrode. So we call that a leave 1 electrode out cross validation. And here are the results. So here for subject 1, these are the true drawings. Over here, we'll look at the scoreboard model. That's probably not very interesting, right? This is our straw man comparison. So this one will predict everything is blob. But look at the axon map model. Now with one set of rho and lambda that applies on all electrodes, you can produce a whole range of shapes. If you're up here, you will predict a streak. If you're closer to the raphe, you predict more of a blob. And I'll show you the same here for the Argus 2 subject. So now you can see that every phosphine is elongated a little bit along the axon pathways, and some are blobbier than others. Why would you get a streak sometimes and other times a blob? Well, it has to do with the raphe. So this one here, this box is the fovea. So the raphe is this horizontal line, remember that? And so if you are close to the raphe, you would stimulate neurons more to the left, right? But there's no way for you to go because the raphe doesn't have any axons. So if you're close to the raphe, you would predict a blob. And if you're somewhere else, like up here, you're actually elongating the streak along the axon pathway.
Another quick question.
Uh-huh.
For subject 2, it seems to me that there are fewer blobs than there are for the other 2, the left drawings, just in terms of the number of directions. Is there a reason for that?
You mean in the model?
No, in the scoreboard model, there's fewer in the scoreboard model than there are in the subject drawings for the axon map.
Oh, I see. I see. So these low blobs, they're also they also count. Yeah, but what happened is, so you fit the data, the model on data from all but 1 electrode, right? And then you might get a tiny row. So when you predict that on the left out electrode, you just get this tiny low blob.
I see. Okay.
Mm-hmm. All right, here are 2 more subjects. Oh, more questions?
Oh, sorry. Yeah. So if you were able to stimulate using 2 electrodes at the same time, maybe picking 2 that are perpendicular to the angle of the arc, do you think that would be able to like force like a more pixel-like pattern rather than the streak?
Perfect. Give me 3 minutes and we'll get to that.
Okay.
We're going there. Yeah, just to quickly wrap up, you can see how different these shapes are, right? Like subject 3 draws exclusively these very long lines, where subject 4 also has triangles and all sorts of things. And you can, to some extent, predict that as well. So how you get a really long line is now your rho is tiny, but your lambda is very long, right? That's how you can predict these streaks. And the length will still vary depending on where you are on the axon map. This will really influence the quality of vision, right, that the retinal implant generates. This is illustrated here. Let's say you now want to present letters and people read the Snellen chart, and the implant might be here over this dashed box. So with just, some small lambda, basically have rho, what that means, you're basically downscaling the image. It might look something like this. But now if you turn up lambda, the streakiness increases. And if you turn it up enough, at some point you will no longer be able to read these small letters. Now, to your point, there's more to it, right? So these phosphines actually combine non-linearly, because what would happen if you now stimulated 2 electrodes that are far away on the retina, but just happen to lie on the same axon bundle? What you would predict is that patients only see one streak, because both of these electrodes activate the same bundle. And in fact, this is what patients are drawing. But what if you now chose 2 electrodes on different bundles? So here, these 2 electrodes are actually closer in terms of retinal distance, right, than up here. But now they happen to fall on different axon bundles. So now you will predict 2 phosphines. And these phosphines might have a different shape. Why? Because this electrode here is close to the raphe, that should be more blobby, and the other one is further away, so that should be more streaky. And so the choice of electrode will really, or combination of electrodes will really influence the shape of the phosphine. At least that's what the model predicts. So yes, if you chose your electrodes carefully, if you understood perfectly the shape that every electrode produces, maybe you'll be able to combine them such that you can produce pattern vision. And so over the years, we have built models to do just that, to predict what bionic vision might look like using these spatial distortions. We also know that the shape is a function of the stimulus parameters. For example, as you increase amplitude, phosphines tend to get bigger and blobbier. But as you increase frequency, for example, of these square wave pulses, you don't increase size a lot, but you do modulate the brightness. And then finally, some animal studies have shown that if you increase pulse duration, you can get rid of some of the streaks and your phosphine should be more blobby again. Unfortunately, spatial distortions is not all there is. There's also a whole thing in time. I won't have time to go through it, but just to give you a sense, intuition of what we can expect in time, we know that the brightness, again, depends on the stimulus parameters. Some phosphines fade faster than others. We know this from behavioral studies where people had to use a joystick to indicate how bright a phosphine is. So here's an example. X-axis is time in seconds. So the dash box here, that's where the stimulus was on for 10 seconds. And the red line here is the brightness. So you can see brightness shoots up as soon as you stimulate. It stays up high. And then when you remove the stimulus, it fades back down to 0. But that only works sometimes. So if you increase the frequency, now phosphines start to fade much quicker. And you can put that to the extreme, where at some point here, the phosphine actually becomes darker than the background, which is kind of odd, something that's darker than black, right? But people get the sense that it's now much darker than it used to be. And then when you remove the stimulus, you get a brief flash, and then it goes back to 0. Of course, this all probably has to do with how ganglion cells respond to electrical stimulation, how cortex interprets this, very complicated, 5 to 10 years of research, and you can put this into the model as well. So now we actually have a piece of software called Pulse to Percept in Python that features some of the most prominent retinal implants. And that allows you now to simulate what vision with these implants might look like, not just in space, but also in time. I wanted to show you some examples. So here is a subway scene in grayscale. And what we're going to do is we're going to downscale this image and feed it into an Argus 2 implant. So with no external activation, we're basically just downscaling to 6x10. And then every the grayscale level of every pixel will be interpreted as the amplitude that you send to an electrode. I'll show this again. It's basically a downscaled version of the video. Okay, now what happens if you turn on the streaks? So here with moderate external activation, you can start seeing some bending, right? Some distortions. And we can take this to the extreme down here. And now everything seems to be elongated along these axon pathways. That was only space, right? So in time, we also know that there can be fading, for example. So this was, again, just a downscaled version. Sometimes things flicker, which is really uncomfortable. So if you just went from one frame, frame by frame to electrical stimulation, you might produce this flickering. And we also know that there is desensitization over time. So take that on top of it, and over time, everything should fade to 0. And that's actually reported to happen in Argus 2 patients. They are sometimes instructed to look into a dark corner, if you can find one, right? And wait a little bit so the system can come back on. Of course, these are only like 6x10 electrodes, right? So maybe we just need more. What if we have more electrodes? Again, for comparison, 6x10 with axons. Let's do 12x20. Now you can see a little bit more detail, but here the external distortions will become very evident here. So now you could see definitely that there's another person walking by, right? It's still not good enough to read a sign in the distance, but it might help you, right, to detect nearby obstacles and indicate the direction of movement, for example. Is this the best we can do, though? Probably not, hopefully not, right? What the model does right now is for a given input stimulus, it will predict what is the percept that they see. But in fact, we need the exact opposite, right? We need the inverse. We need to know for a desired percept, what is the required stimulus? To show you some examples. As a very first baby step, we can think of this as a regression problem, right? We're trying to minimize the error between a target output, say the letter E, and the predicted output by the model. Currently, if people want to produce the shape of E in the mind of the patient, they would imprint E on the retinal surface, right? If you think of this as a pixel display, you would just draw the E on the retinal surface. But we could use the model now to tell you that won't look anything like an E. It might look something like this. And instead, what you want this side to look like E, right? So if we find the stimulation pattern that minimizes the error between this predicted output and the target output, we get something that looks much more like an E. But now just by looking at the pattern of stimulation here, you can no longer tell what the shape is going to be. But that's okay, because now we're using knowledge about the axon map. We know if we stimulate here, it's going to smear out to the left, right? And we can incorporate that into our prediction and kind of make the axon tree work for our purposes. In addition, this improved optimized protocol is sparser, right? You only need this guy, that guy, and a little bit in between. And you also take into account, as I just mentioned, the knowledge of the axon map. Here's another, yes.
There's consistently kind of seems to be like this horizontal dividing line between the top and the bottom. Is that a consistent thing that people get with the implants, or because that's not, I'm assuming in natural vision, it's not so cut off between the top and the bottom, right?
Yes, yes. So as far as I know, if you stimulate here, people will not report something like this. They will only report the bottom half. But you're right, in natural vision, it might not be as clear cut as this. This is probably over here. This is probably an artifact of the model. I'll give you that. But it's really hard. It's really hard to measure.
Sure.
All right, real quick, here's another example. Would anyone like to guess what letter this is? Either in the chat or using your voice. Any wild guesses? If you're still awake. V? S? Yeah, pretty good guesses. Unfortunately, it's an N. So this is what will come out if you put an N on the retina. Whereas if you search for the optimized protocol, you get something that looks much more like an N, but there's still challenges, right? So you can see, for example, it's really hard to draw a line perpendicular to the axons. Why? Well, if you stimulate here, it's always going to smear out to the left, right? So it's really hard to produce here a vertical line that you need for the N. And then a last example, this could be anything, right? Maybe a C, but it's really not, it's a Z. Whereas here, if you optimize again, you get something that looks much better, but still not perfect. So I mentioned already, right? Another thing to keep in mind is that amplitude, for example, it changes the size of the percept. And so if you want something in a particular shape at a particular brightness, that might be really hard to get. And you might have to choose your amplitude and frequency very carefully. So yeah, overall, this is still very challenging, but at least there is a possibility, right? That we can produce shapes that are more recognizable than what is currently being done. So we've been trying this with Argus 2 patients. Unfortunately, COVID kind of messed with us, so it's still ongoing. What we really like to do is to use the conventional protocol as is, and then compare the shapes to our optimized protocol that is fit to every patient, and demonstrate that you get better performance with the optimized protocol. In the future, of course, you want to expand this. It shouldn't just work on letters, right? It should work on pretty much any shape. So there's, yeah, a lot of work ahead. All right, in the remaining time, I wanted to highlight another problem with the current devices, which is that they cover only a very small portion of your visual field. It's never the case, you know, that you just see the subway scene and you can fill out your entire visual field. No, like Argus 2 only spans maybe 10 by 20 degrees of visual angle. That's like, you know, watching TV from across the room. And so as a consequence, people have to learn to use these devices in a very specific manner. They're bodily techniques, namely head scanning, as it's called. You have to think of your head as a spotlight, sorry, a flashlight. Well, spotlight works too, into the world, and you have to move your head, right, to illuminate different portions of the scene. On top of that, you get these flashes of light, right, as it's described, which look nothing like natural vision from what we know. And so there's a step of associative learning involved. You have to learn to associate meaning with these shapes, right? So maybe you know you're outside and you see this vertical flash of light, and then you look up and you see this glitter, this firework. Then maybe you're standing in front of a tree where you first looked at the trunk and then you saw the leaves and the light reflecting off of it. Does this over here look like a tree? Nah, debatable. But you know, using deductive reasoning, you can figure out what you're actually looking at. And so this is very hard to simulate on a screen, right? Especially since the way these devices are evaluated is usually by taking 3 steps ahead. Maybe you'll be asked what letter is presented to you on a screen, but more often than not, these people are asked to, you know, walk across the room to a door or follow a line on the floor. So these are all behavioral tasks, right, that involve walking around, moving your head, moving your eyes, and so on. And so all of this is really hard to simulate on a computer screen. But virtual environments offer an elegant way to solve many of these difficulties. For example, in VR, it's very easy to generate different stimuli, right? Different objects, different environments, whatever you want. It's easy to gradually increase the complexity of the task. whereas in the real world, some tasks are just impossible for these patients to do. It's also easy to incorporate auditory or haptic feedback. And what that really says is that what we should do probably is build a virtual patient, which is someone who would be viewing these bionic vision simulations through a virtual reality headset. And you could walk around in the virtual environment and use the phosphines that you see to do the same task that people would use to study Argus 2 performance. People have been doing this for a while, so have we. What we have currently is a system that can be fit to an individual patient. So it starts with the fundus images of an actual patient, so we can get a model, an axon map model out. We can stimulate the exact same way that Argus 2 would stimulate, and we can recreate the environments, the exact environments used in other behavioral studies. So really, for every one of these steps, we have like a virtual equivalent. And that allows us to build what we call a virtual patient, which is really, it's a sighted participant wearing a VR headset and looking at these biologically realistic models of prosthetic vision, as I've shown you in this talk. As I mentioned, this can be fitted to an individual patient, and it can be used to recreate some of the behavioral studies that we've seen. As an example, for example, now we can ask how behavioral performance would be affected by, for example, the level of immersion, right? Are you just looking at stimuli on a screen or using a headset? And also by the severity of these spatial distortions, namely rho and lambda, because we know different patients have different rhos and different lambdas, right? So that probably affects their performance. Now we have a way to test that. We did that by re-implementing two classical tasks performed by Argus 2 users. One is a visual acuity task that's less immersive, right? You just see a letter on the screen, you have to say which one it is. And the other one is an obstacle avoidance task where people had to walk down a hallway and avoid people. These people could pop up in any one of these locations. And so we were able to recreate this environment in VR using the exact same dimensions and all. Real quickly, here is the visual acuity task. So the way it works is you're sitting in front of this laptop. You can see the participant view. Usually people turn off the lights. In the real ones, we did that too. So you really only E sticks out. Then the implant usually would pre-process the image, maybe extract or enhance the edges. And then that is what is fed into the axon map model. Now we can mess with rho and lambda, right? We can make it really small, really big. If you have this one up here, if your lambda is really small, you basically have a scoreboard model. So in the literature, typically this is what people are using to simulate these devices. But we all know now that what most people see doesn't necessarily look like this, it might look like that, or if you crank it all the way up, then you shouldn't be able to see much at all, other than just, flashes of light. So we wanted to see how these different conditions affect performance. We also compared to larger arrays. So looking a couple of years ahead, what if you had a 10 by 16 or a 19 by 31 electrode array? All right, and here's an example of what that looks like. This is the poem. Here you see the subject sitting in front of the screen. They see the letter on the screen. They can use their head and the headset will update the scene. Here's an example. It's kind of fast. So they see a letter, they can look at it from different angles, and then they have to select from this wheel, they have to select the correct letter. So here, this is now, T, let's select T, there we go. This is C, that was really fast, so on and so forth. And what we found is that, first of all, not surprisingly, if you increase lambda, make it more streaky, people get worse at letter recognition. So here we're showing the F1 score, which is a combination of the precision and recall. So the higher, the better. 1 is the max. And we show the F1 score for different lambda values. Lambda 50 is basically the scoreboard model. So there, people are really good at the letter recognition, both in the headset version as well in the monitor version. But now, as you increase lambda, you get this drop in performance all the way down to pretty much chance levels. With rho, just the size of electrode, we didn't find any significant effect except for these two here, meaning that what really drives performance seems to be the length of these axon streaks. On top of that, if you increase the number of electrodes, you get some performance improvement, especially from 6 to 10 to the middle one here. But then as you increase further the number of electrodes, you only get a modest performance increase. So again, it seems that the driving factor between performance differences is the length of these axon streaks, lambda. And that's important because every patient has a different lambda. You just don't know which one it is, right? So if you just look at letter recognition, you don't really know where you are in this plot for a particular patient. Okay, finally, this is comparing HMD headset versus monitor version, and we don't see any significant differences across all the conditions. Not surprising, right? Because you're basically sitting in front of a screen, so you might not get a benefit from wearing a headset there. But what about the second task, the hallway navigation task? So again, as a reminder, we re-implemented this paper, the environment from this paper. You had a hallway. You start here, you have to walk to the goal line, and there could be objects, people popping up in one of these locations. This is what it looked like to the participant. This is what it looks like if you extract edges. And here's a little shot of the real environment. I'll show you a bigger one in the next slide. This is basically what it looked like to the patient, the subject, for a particular setting. You see lambda is kind of long, right? It's all streaky, and you can see the edges of the room. Now here, there's a much more intense version where you have large rows and large lambdas, and the task basically becomes impossible. All right, here's what it looked like in the lab. We had these ropes where people could hold on so they wouldn't trip and fall. So the goal was to walk along, you can see here the first person view, along the hallway all the way to the other end. And now you can see what it looks like with bionic vision. Much harder now. And this is just a scoreboard model. All right. Unfortunately, neither of the settings, any of the settings made a difference. Subjects were always at chance levels or hovering around chance levels, which is also what you find with real Argus 2 patients. So no matter the setting of lambda, no matter the setting of rho, no matter how many electrodes, you always hover around chance levels. With the headset, you were better, slightly better than on the monitor, but still you were not better than chance. And so this really points to another unsolved challenge, right, in this field, which is how can we make these devices useful in real world tasks? Sure, a more immersive simulation may benefit performance. We know distorted phosphenes may impede performance, and that is useful, right, for to provide realistic predictions of, let's say, Argus 2, for example. But the big open question is, how can we improve the performance on real world tasks beyond chance levels? And we have a lot of fun ideas. One is to really make use of all the computer vision literature that has come out recently, because with the advent of deep learning, it's possible to segment objects in your environment on a single frame basis. It's possible to extract depth, which could allow you to highlight only nearby obstacles, or to outline the edges of a room so you know where you are in relation to the room. And then there's even more fun things which I haven't seen applied to bionic vision yet. One is called visual question answering. So the way this works is you input a sentence, a question, how many giraffes are drinking water? And the deep neural network will then respond visually. It will draw a bounding box around the giraffes, but not all giraffes, right? Not this one, only the ones that are actually drinking water. Now, I don't know how many Argus 2 users have giraffes at home, but of course, the application would be, you could ask, hey, where did I put my keys, right? And as you scan around the room, if the bionic eye picks up the keys, it would outline them. And so there are many useful cases in everyday life where people might need help from a bionic eye, and the bionic eye could respond specifically to that particular problem. And so that's kind of where we're heading as a lab. We're very excited to get started on this next generation, basically, of implants. And so I'll leave it at that. Be happy to talk more if you have specific questions. I wanted to thank my team of students, which is really interdisciplinary across many different departments, including computer science, psychological and brain sciences, neuroscience. I also wanted to thank NIH for funding this research. And finally, if you're interested in getting in touch, we actually have an open position for someone with a bachelor's degree who's looking for a gap year before they start their PhD. And I'll leave it at that. Thank you very much. And I'll be happy to take your questions.
Thank you. I guess if anyone wants to jump in with questions, feel free. And
yeah, I have a question. First, I really enjoyed the talk. Thank you very much.
Thank you.
My question is, you mentioned that pulse duration decreases the tail. Like if you increase pulse duration, you decrease those tails.
Yeah.
And I was just, is there like a mechanism or proposed mechanism as to how that happens? I mean, it kind of seems like for that to happen, there would be less stimulation of the same cells on that fiber. Is that what happens from increasing pulse duration?
Yeah, first of all, most evidence comes from animal models, because Argus 2 does not allow us to increase the pulse duration to a point where you could see that effect. But the mechanism that is proposed is that with these longer pulse durations, you're now closer to the preferred stimulation frequency of bipolar cells. So you activate ganglion cells and their axons less, and instead activate bipolars, which then in turn activate ganglion cells.
That's very interesting. Okay. So, and I think in cortex, there's been some work about anodic leading versus cathodic leading pulses and different sensitivities to exciting cell bodies versus axons. Is that something that's been tested here too?
Yeah, I don't think I have a slide for that, but there's a couple of papers that are concerned with the waveform, basically. And there's some cool work out of Jim Weiland's lab, for example, at the University of Michigan, showing that, yeah, if you lead with anodic and you made the pulse asymmetric, you can reduce the threshold current, for example. If I remember correctly, it looks something like that. And there's variations of that could also lead to different streakiness, I guess.
Okay. So the one you just drew, that would be better at stimulating the cell bodies rather than fibers? Is that? No?
Yeah, I might be misremembering. I think this one reduces the threshold current for sure. And okay. I'm not sure about the streakiness.
Okay, thank you. You said it was Jim Weiland?
Jim Weiland. I can put it in the chat.
Thank you.
Yeah, you should definitely look him up. He's one of the big ones in the field.
I guess I have a question, kind of more general. So you talk about kind of this, we have a certain image we want to project, and then you do this like error minimization to figure out what the best stimulation pattern is. So the question kind of has to do, is there an analogy for this in biological processing, or is this transformation in processing due to the fact that you're trying to give the same image with fewer electrodes? Like how is this done biologically, or what's the mapping here?
Yeah, I see. It's I think of it as solving a black box problem, right? So you have light coming in, there is this complicated dynamical system that produces vision. And the way we can get at it is by having these behavioral data, these drawings, these brightness curves and stuff like that. So by knowing this transform, this black box here, we can make use of it. We can learn that, maybe it's better to stimulate here and over there. and if we do that, we can form complex patterns. So in a sense, it's without necessarily identifying the neurophysiological mechanisms, it's getting at the transformation of light to perception, if you will, right?
Right.
And we're trying to find better combinations of stimuli.
Yeah, but I guess biologically, like you're doing this at the retina, like the stimulation at the retina. So is the assumption that in regular biological vision, this process is happening pre-retinal? Because that's kind of where your insertion point.
I see. Yeah, okay. I mean, if you have perfect precision, what you would want to do is you would want to know, if I present a certain image, how does the population of retinal ganglion cells respond, right? And you would know everything on and off and every pathway. And then you would mimic that stimulation pattern with electrical stimulation.
Right.
And some people are working towards that. There's a E.J. Jichelniski at Stanford. The problem is you really need single cell resolution, right, of in terms of electrodes to get to that, or at least, small population level of resolution, which we do not have with Argus. So in a sense, we are not making assumptions there. What we know is based on behavioral drawings, people being blind for 40 years and these electrical stimuli being so different from natural vision. We're just learning what the transform is. If you stimulate here and there, what will that look like? So underneath it all, sure, there's like a population of V1 neurons that interpret the incoming signal, right, that you send to the ganglion cell axons. And you could mimic that code, but that's really not what we're doing here because we're not at that level of resolution.
Yeah, okay.
Does that make sense?
Yeah, I think so. All right, we had one question in the chat and then a hand raise. Let's start with the chat.
Okay.
Question. Do you want me to read it to you?
Sure.
All right. Is there any use in the literature of idealized mechanistic, for example, conductance-based Hodgkin-Huxley models of retinal axons to, for example, reproduce and characterize the nonlinear responses of the cells, even heterogeneous, to a range of stimulus profiles?
Yes, I think that has been done. I mean, Professor Ratte is probably has been doing this for a very long time. So you can have like a multi-compartment model of axons, Hodgkin-Huxley style, and measure how neurons respond to electrical stimulation. I think the challenge there is, this has been done for single neurons, but to do this for a whole population of morphologically distinct neurons in the retina is really computationally challenging. And then even if you do that, you don't know what perception results from that because, blind retina undergoing degeneration for a long time, it's going to be really hard to build a computational model that is faithful to the physiology of such a system. But it has been useful to experiment with different waveforms, for example, or to elucidate that it's really the axon hillock, right, that initiates the spike. And maybe there's combinations, that'd be the dream, combinations of stimuli, applied at certain points on the axon that will get rid of the streaks, for example, something like that would be awesome. But I'm not aware of, anyone having achieved that.
Great. Akwasi, do you want to ask a question?
Yeah, hi, Mike. Great
Hi.
presentation. Just kind of followed your work a little bit. I was at Jim's lab sometime in 2020, so kind of familiar with what's going on. Back onto what Mark was asking about all of the activity happening, recognition happening pre-retina or the retinal site. Wouldn't you consider, some form of retinotopic mapping from, the retina to the cortex inside your model, to sort of, so that's something to, think about. And the second question that came up, I think Dr. Weiland also has a paper that came out sometime 2 years ago that models, single cell electrophysiology and tries to hook up a couple of them together to get a tissue level propagation. I know the first author to that is Kate Finn. So if folks care about, that, they could look it up.
Yeah, that's a good one. Yeah, that was the okay, now I can't remember what it's called. The patient-specific framework for Argus 2 patients, something like that.
Yeah,
that's a great paper. Yes. And now, of course, I forgot your first question. Retina topic map. Yes. Right now, we're just assuming a one-to-one mapping from retina to visual field. Yeah, that's probably not true. But the mapping is not as distorted as in visual cortex, right? There's no cortical magnification yet. You probably, you do have different ganglion cell densities across the eccentricities. But so far, the data we have, these drawings, they're just not precise enough for us to see a difference. We've tried some other retinotopic maps, and the drawings, the data we have are not precise enough to rule out one map over another or to even fit it to an individual patient. So long story short, we're going with one-to-one right now. We know it's not completely accurate, but so far it's been good enough.
Yeah, thank you.
I have another question.
Uh-huh.
Yeah, so it's kind of one of the things that we learn in neuroscience class about vision is that it's not like the visual world we see, it's not like it's just what the whole eye is seeing at one given time. It's constructed over time by microsaccades and saccades by the fovea. So in Argus 2 patients, is there kind of like remembering of the artificial stimulus that they saw, and that's like somehow like integrated into like the kind of time average view of the world, or is there anything like that going on?
That's a great question. I would love to know the answer to it. Right now, Argus 2 does not allow for that level of precision again. That's something we need to change, I think, going forward, because there's all this work for BCIs as well, right? That show that vision happens at a certain phase, right, of different brain oscillations. So maybe that's something, that would also change the quality of vision, even in the retinal implant or a visual cortical implant when you deliver, and then over how many cycles, right? If there's really something, if this temporal integration is essential for perception, then right now, we're just not even at the same, in the ballpark, of precision. Right now, it's really just, let's stimulate a bunch of neurons. By the way, I haven't even talked about eye movements, right? Our Argus doesn't care about that either. So it doesn't matter where you look, you will always stimulate the same neurons in the retina, which is horribly confusing because the brain works with an efference copy to tell you where you're looking. And so there's many intricacies, right, about the neural code, about how vision works. We could do a better job taking into consideration when we stimulate. That has not been the case so far. I hope that in the next generation of implants, we will be much more considerate and nuanced in our approach.
Gotcha. Thank you very much.
Mm-hmm.
All right. Well, I guess we can probably stick around and talk a little bit more, but I'll end the recording for now and thank Dr. Beyeler for the talk. It was really interesting and informative, so we really appreciate it.